When most of us hear the word robotics, we tend to picture scenes exactly like this: a high-budget sci-fi machine navigating a futuristic landscape. But take a look at this image of an active automotive assembly line. This is where real automation lives. It is a practical, highly coordinated system of robotic arms driving daily global manufacturing. The common ancestor connecting those two extremes is a machine you can hold in your hand, the line-following robot. The leap in scale between education and industry is entirely a matter of hardware. A classroom robot tracks black electrical tape across a desk, while a heavy-duty warehouse vehicle follows magnetic strips embedded in a concrete floor to move thousands of pounds of inventory. The mathematical and mechanical rules governing the Fourth Industrial Revolution are completely accessible. You don't need a secret lab to learn them. You can build them yourself for the cost of a few basic components. The primary physical objective for any line follower is strict compliance. It has to maintain a precise trajectory along a defined path, no matter what environmental variables get in the way. To pull that off, the machine needs eyes. These are typically optical or infrared sensors mounted underneath the chassis, pointing directly at the ground. The sensor emits an infrared beam downward, measuring the bounce back. It registers high reflection on white and total absorption on black. To calibrate, we set a threshold data line halfway between them, establishing a binary trigger point. Autonomous sight at this foundational level has nothing to do with human vision. It reduces a chaotic physical environment into a clean, manageable stream of light and shadow. Those light readings are sent straight to the robot's brain. This macro photograph shows the surface of a microchip, similar to the accessible microcontrollers, like an Arduino Uno, that receive and process the raw sensor data. Programming that brain is actually just writing a continuous, high-speed loop of basic questions. The code is entirely built around asking, "Am I on black? Am I on white?" thousands of times a second. Getting that logic wrong in the physical world carries a risk. If you cross a wire or send too much voltage through a breadboard, you will quickly burn out your components. To bypass that hardware risk, students use free digital sandboxes like Tinkercad. They test logic circuits virtually, proving the code works before a single wire is cut. Artificial decision-making boils down to this high-speed feedback loop, perceiving a single variable, checking it against a programmed rule, and preparing an immediate electrical response. That electrical response is pushed out from the microcontroller down to the robot's feet, its motors and wheels. This top-down schematic illustrates the physics of correction. When the left sensor detects a drift, the microcontroller signals the opposite motor to increase RPM, physically angling the chassis back onto the correct path. If we increase the mass for an industrial transport, the motor's response must be programmed differently to stop the heavier object from overcorrecting. The physical shape and weight of a machine dictate its specific job. The underlying mathematical algorithm of continuous error correction remains exactly the same. This archival photograph shows Unimate robots on an early automotive line. The exact same high and low binary signals that a student uses to blink an LED on their desk are the fundamental logic blocks powering global manufacturing. Shifting focus from the machine to the human, building a line follower acts as a gateway into project-based learning. This image captures a modern robotics competition in a high school gym. It is a high-stakes environment where students develop logical mathematical reasoning, resilience in troubleshooting, and the ability to collaborate under pressure. This photograph of students learning to solder proves that the demand for hands-on, practical technical education has always existed. Today, that same experience is supported by professional-grade simulation and microchips available for less than the cost of a standard textbook. Building these machines no longer requires an industrial-sized budget. When the same binary logic is shared between a $30 classroom kit and a global assembly line, the path to understanding robotics becomes a series of practical, logical steps. Let us know in the comments if you want a step-by-step tutorial for your first build, and subscribe for more deep dives into the systems that run our world.